somewhere, see, after 1 or 2 steps in that column wise, somewhere 1 or 2 elements I am missing them. I'm not getting the exact answer where I'm lagging. So if I want to refer any book or that, I don't have any such books. And if you please refer any book so that we can go through that, sir, because these 2 weeks are basically graphs.
Yes.
That's why, sir.
Okay, just give me a minute. I will probably.
Okay, okay.
I'll
Okay, sir.
share the name of that.
Right. Thank you.
Oh. Okay. Anyone else like any? I guess.
Sir, I have doubts in many of the graded assignment questions because I covered the lecture video, but when we come to solve the question, I found it very difficult.
Okay, fine. We'll come to that also. Okay. Okay, so again, I guess Yogendra Pandey, what is your problem?
Yes, sir. I have watched all lectures, but some algorithms I don't.
Okay. Okay, so then, okay, let's get started. So probably I'll start with maybe some of the easy things probably. So I'll come to this Bellman-Ford and Floyd-Warshall algorithm little later. First, I'll maybe start with the spanning tree. Okay. Link is not working. Okay, I'll inform the team.
Sir, also one more thing, in last class, Shrikant sir told the graded assignment date is extended to 27. So
but it will not extend.
Yes, I have to solve all the questions in last.
Yesterday it was so hectic, sir.
Yeah. So the thing is,
only one session for week 11.
Yeah, so basically we also like so in the beginning we planned to extend the deadline for week 11 thing. So but okay, so because of some problem actually we are not able to extend that deadline. Okay, so let me start. Okay, Subha, I guess. Subha.
Yes, sir. Subhasish, sir.
Yes.
Yeah, sir. I'm first time here. Sir, I don't know how to join this meeting through the peer deck, sir.
But this is not happening in peer deck. This is basically it's a Zoom. Okay. Zoom session, right?
Okay, sir.
Yeah.
Thank you.
Okay, so.
Sir, and for grading, sir, the best of how many assignments will be considered for grading?
Maybe 6 or 8, I guess. Can one of you answer this one?
7.
7, right? Okay, 7, yeah.
That's 7 of 12, sir.
Yes.
11,
not 12, it's 11 because in week 12 actually we are not going to release anything. Okay.
Okay, sir.
It's more or less. It's more or less a
7 of 11.
Okay, sir. Okay, got it.
So that's it, sir. Means one more content will it be released or?
No.
In week 12 revision part.
Week 12 is so basically since actually so initially the deadline of week 11, I guess it was on 24. Okay, so since we planned actually not, so since there was nothing for us to release in week 12, so that's why we initially planned to extend the deadline of week 11.
That's what Srikanth sir told.
Yes, but okay, so but it was more or less we informed that, but somehow it was not possible for us to extend that deadline. Okay. Okay, so let me start. Let me share my screen and okay, so I guess someone asked me about the book, graph theory book. Like I
Yes, sir.
I forgot. Actually, Srikant shared this name of the book, I guess, in discourse.
Sir, one of the session you will told that Rosen.
No, Rogen, it's not for the thing is, it's Rogen. Actually, you will not get all these things. Like there are, in Rogen graph theory, it's more or less some kind of classical graph theory.
In Amazon, I checked few books, sir.
Mm-hmm.
Yeah, will the book Graph Theory for Engineering and Computations, will it be helpful, sir?
No, just a minute. No, so the main problem is actually you cannot most likely in a single book. It's difficult for you to get all the things.
Okay, so many books we want, reference
Yes.
books.
So no, so for BFS and DFS, okay. So this thing actually you can get maybe some engineering book, okay, but I don't know about the week 11 concept, like this algorithm. All this algorithm, whether you will get in a engineering book or not. But BFS and DFS, these are pretty standard, so most likely you will get in any book. Okay, so not certainly not in Rogen. Okay.
Achha.
But in some engineering book, probably you can get it.
Someone gave one message. Handbook of Graph Theory. Yeah, I'll go through that, sir. Okay, thank you.
Okay, fine. Yeah, so maybe in this book, maybe probably you can get all these things. Okay. But Srikant, I guess he said something else. I'm not able to.
Srikant sir said
Bondi and Murthy.
Yes, that one. Okay.
Bondi and Murthy.
Bondi and Murthy, yeah, correct. Okay, so let me share my screen. Let's start the session. Okay, so you can see my screen, right?
Yes, sir.
Yes,
okay,
sir.
so okay, so let me start with the EG one. Okay, so the main thing is the main idea is to find a spanning tree for a connected graph. Okay, so we want to find a spanning tree for a connected graph. Okay. So to find the spanning tree, so basically, okay, let me recall what do we mean by spanning tree. Okay, so spanning tree is basically it's so for a graph G. So suppose I have a graph. Okay, suppose I have a graph G. So graph means basically we have set of vertices and we have set of edges. Okay. So for a graph, the spanning tree is basically we need to find a tree. Okay, so we need to find a tree such that it connects all the vertices. Okay, for example, if my graph is this, let's say this is my graph, this is 0, 1, 2, 3. Okay, so this is a connected graph, right?
Yes, sir. Connected undirected graph.
Connected undirected graph. Okay, so what actually we need to do? We need to find a tree. Okay, so basically we need to form. So you need to convert this graph into a tree, because now it's not a tree, right? Because you have a cycle here. Okay, so if you see, you have a cycle here, right? Okay, so you have a cycle here. So what we need to do? We need to convert this graph into a tree such that that tree actually covers all the vertices. Right? So that tree has to cover all the vertices. So if you see, if I remove one of the edges, right? If I remove any one of the edges, then this graph will become a tree, right?
Yes, sir.
So suppose you want to remove. So if I want to remove, let's say I remove this edge. Okay, then now this new graph, it's a tree, right? It's a tree. It's a minimal. So it's a minimal. But what is the definition of tree? Anyone?
Minimal connected acyclic.
Correct. It's a minimal connected acyclic graph. Okay. Yeah. So and you know, like if G is a graph with n vertices, so then if you form its spanning tree, then it will have n minus 1 vertices. Sorry, n minus 1 edges. Okay, so here we have 4 vertices, and as you can see, we have 3 edges, right? So this is for a non-weighted graph, right? So this is for a non-weighted graph. But what we want? We want minimal tree for a weighted graph. Okay. So for weighted graph, it does. So for weighted graph, we want to find minimal tree. That means if I add the weight of all the vertices, then it has to be the minimum. Okay. For example, let's say the weight of this edge 0, 1, it's 2, right? And the weight of this edge 1, 3, it's 5. And the weight of 2, 3, it's 7. And the weight of 0, 2, it's 1. Okay. So now, if I consider this, so if I consider this tree, so now here, what is the total age of this tree?
14.
14, sir.
2, 5, 7, right? This is 2, 5, 7. So the total age is 14. So now, instead of considering this tree, if I consider this one, right? If I consider this one, 1, 0, 2, and 3, right?
10, sir.
This is 10. So as you can see, this particular tree has weight less than this one, right? Correct?
Yes, sir.
So what we need to do for a weighted graph, we need to find a tree such that the weight of that tree is minimum. Okay. So we need to find a tree, spanning tree, such that the weight of that tree is minimum. Among all the possible trees, that weight has to be minimum. Okay.
So for this one, we can make it as like this also, right? 0, 1, which is having the weight of only 8. So 0, 2, 0, 1, and 1, 2, 3.
So can one of you tell me what will be the minimum spanning tree for this?
8.
8, sir. 2 to 3. 2, 0, 1, 3.
8. 1 plus 2 plus 5.
So if I consider this as let's say this one, and this one, then this will be the minimum spanning tree, right?
Yes.
So this is the minimum spanning tree for this graph, because as you can see, the total weight is basically 8. Okay. So to find the minimum spanning tree of a graph, okay, what you need to do? So there are two algorithms, and using these two algorithms, we can find the minimum spanning tree of a graph. Okay. So the first one is Prim's algorithm. Okay, so so suppose you have a graph, let's say. So I'll solve, maybe I'll first I will take the example that Sir has given, and after that I'll try to solve some of the activity question. Okay, let's say this is the graph. And the weight of this edge is 18. This is
17.
10. This is 6. This is 70. This is 28. 8, right? So in Prim's algorithm, what you need to do? First, you need to choose a edge. Okay. So what edge first you need to choose? You need to choose choose a edge with smallest weight. Okay, so overall you have to choose a edge such that the weight of that edge is smallest, right? So can you tell me who among all the edges, which edge has
3 and
1, 2, 3.
1, 2, 3, sir. 1, 3.
1, 3, right? Right. So this is the edge first we need to choose. Okay, so this is the edge we need to. Right. So then what we need to do? Then we have to extend this tree. Okay, we need to extend this. So now this is my first step. Okay, this is my first step. Okay. So now what I need to do to find the spanning tree, I have to extend this one. Okay, whatever I have now, this edge, I have to extend it. So next what we need to do? We need to go for the edges which are connected to this edge, right? So how many edges that are connected to this edge? 1, 3.
1, 0.
3 edges which are connected to one.
Yeah, 3 edges.
Not 3, I guess. I guess 4.
4.
Right?
Yeah, 4. Yeah.
Because this says 0, 3. This 0, 3 is connected to, and also 0, 1 is connected to 1, 3.
Yes.
3, 4 is connected to 1, 3.
1, 2.
And 1, 2 is also connected to 1, 3. So after that, what we need to do? So how we can extend this one? Next, among all the edges that are connected to 1, 3, we have to choose the edge of smallest weight, right?
Yes.
So then what is my next choice?
1, 0.
1.
0, 1, because this edge has weight 70, this edge has 18, this edge has weight 10, and this edge has weight 20. So among all the weights, now you can see 10 is the minimum, okay, or 10 is the smallest. So next I have to take this edge 0, 1, right? 0, 1. So next, if you see the neighbors of this new edge 0, 1, it's basically what? 0, 3, right? Correct. What is the neighbor of 0, 1? 0, 3 right? Or 1, 2, correct?
Yes, sir.
So basically, I'm not adding any new edges. Correct. So previously I had 0, 3, 3, 4, and 1, 2, and 0, 1. So after adding 0, 1, I am not getting any new edges, right? So I have I have 3 edges. That is 0, 3, 3, 4, and 1, 2, right? Correct or not? So now I have 3 edges, right? 0, 3, 3, 4, and 1, 2, correct? So
Yeah.
among all 3 edges, which has minimum weight?
1,
1, 2.
1, 2.
No.
0, 3, sir.
0, 3.
0, 3, right? See, previously in the beginning, if you see, previously if you see, I had 3, 1, right? And the neighbors of 3, 1 is basically 0, 3, 0, 1, 1, 2, and 3, 4. Okay. What I have done after that, I have added this 0, 1 because 0, 1 has minimum edges. The 0, 1 has minimum weight. Okay. And once I add 0, 1, okay, I'm not adding any more edges. Okay. I'm not adding. So basically so I'm not getting any new edges, which is neighbor of 0, 1. Okay. Now I have the same set. Okay. So in this set, this 18, I have this edge has weight 18, and this edge has weight 70, and this edge has weight 20. And among these 3 edges, the minimum weight is 18, right?
Yes, sir.
But the problem is I cannot connect this edge in my tree, right?
Yes, sir.
Because
Yes,
because if I connect, then I will get a
Cycle.
cycle.
sir.
Okay, so then I have correct. So then I have to exclude this edge. So what is my next choice?
1, 2.
I'm left with, so basically I'm left with 2 more edges, that is 3, 4 and 1, 2, right? So but the problem is I cannot, since 1, 2 has the smallest weight, so then I have to consider 1, 2. Okay, I have to consider 1, 2, correct?
Yes, sir.
So now what are the neighbors of 1, 2?
2,
2, 4.
4 and 3 to 4.
Sir, only 2, 4.
only 2, 4.
Only 2, 4, because see, I have, so there are so many neighbors of 1, 2. One is 0, 1, one is 1, 3, and another one is 2, 4. But we have already included 1, 0 and 1, 3. Okay, so only new neighbor is 2, 8. Okay, correct. So
Yes.
now we have, now in our checking list we have two edges. The one edge is 3, 4, okay, and one more edge is 2, 4, right? 2, 4. So among these 2 edges, 2, 4 has minimum weight, right?
Yes.
So then what I need next, what I need to do, I have to add 2, 4, right? And now if you see, now basically so this is a tree, right? And now we have included all the vertices, correct?
Yes, sir.
So then this is now this is a minimal spanning tree. This is a minimal spanning tree, correct?
Sir, in the last step,
Yes.
To the edge 1, 2, there is only one connected edge, no, sir? 2, 4.
1, 2.
Yeah.
No, see, if you see there in 1, 2, so there are 3 edges, right? 0, 1 is also connected to 1, 2.
That is already included.
But we have already included.
Yes,
that.
sir.
Okay, so the only new edge we are adding
Be
is
able to
basically
see is 2, 4.
2, 4. Okay, see 1, 2 has three neighbors. Okay, but we have already included these 2 neighbors, 0,
Yes, sir.
1 and 3,
Yes, sir. Yes, sir.
1. Okay.
Sir, but for each time we have to look into for each vertex, both the ends, no sir, 2 vertexes, neighbors of the 2 vertex. Like if 1 to 2 means we have to look into neighbors of 1 as well as neighbors of 2.
Yeah, that is what.
Time.
Yeah, that is what we are doing, right? So when I said 1, 2, 1, 2 has 3 neighbors, then basically I'm checking this endpoint 1 as well as endpoint 2, right?
Yes.
Yes.
Got it. Thank you.
Okay, so let me solve one questions from.
Starting, we have taken comma. Why in the starting when we calculated 0,3 and then we can move to 3,4 and then from there we can move to 4,2. Why haven't we taken that due to that weight?
Sorry, can you repeat? So we have started with 1,3, right?
Yes.
Yes. Then after that, so we have started with 1,3. Okay. After that, we have added 0,1, right? So what is your question?
My question is why
started 1,3? Why not others?
No. So the
because that is the minimum weight.
So for the Prim's algorithm, you have to start with the smallest weight. Okay. So you have to start with a S that has the smallest weight, right?
But so how we can say that 1,3 is small weight?
No, because the weight, what is the weight of, see how many edges you have in this graph? You have 0,1
and 0,3 and 4,3, 4,2, 1,
so what is the age of 0,1? What is the weight of 0,1? 10, right?
Yes, sir.
What is the age of 0,3?
18.
18, right? What is the age of 1,3? 6.
Yes, sir.
So what is the age of 1,2? 20, right? Then you have 3,4. The age is 70, and you have 2,4. The age is the weight is 8. So which age has minimum weight here?
1,3.
So then you have to look at the graph, and from by checking weight of all the edges, then only you can decide which edge has minimum weight. Okay.
Sir, sir, if age 0,3 has a weight, suppose 5, then we should start from 0,3 age.
Yes. You should, if instead of 10 here, instead of 10, if I write instead of 10, if I write this is 2, okay, then I have to start with 0,1 instead of 1,3. I have to start with 0,1. Okay. Let me.
Sir, but 1,3 is the most common age among the graph.
No, that is not the, that is, you see, that is not the not in so that is how Prim's algorithm is defined. Okay, you have to start with the minimum smallest weight.
Okay, sir, got it.
Sir, one last doubt, sir. Sir, here we have totally 6 edges, but we end up with only 4 edges because in Prim's algorithm tree we have n-1 edges only. So we should stop with that, even though if there are more edges.
No, here we have 5 edges. Sorry, not 5 edges. We have 5 vertices, right?
5 vertices. That's why we stopped with 4 edges.
Yes, correct.
Even though we are not visited with the 2 vertices, even though that it is existing that, no sir. In the original graph there are 6 edges, no sir. So but is that okay, sir? I mean,
no. First tell me.
For all.
No. If G is a graph, okay, G is a graph with n vertices. Okay.
N vertices.
Then what will be the?
We should have n-1 edges.
Yes. In that tree, that minimal spanning tree, you must have n-1 edges. Yes. So then you can see, right? This has 1, 2, 3.
In the same 4. Graph, if they ask to find us how many spanning trees are possible, then how can we do that, sir?
No, it's depend on the question. Like certainly, it's not easy for any graph. Since I guess you have a question like for inactivity, right?
So yes, activity, yes, sir.
Yeah, that is actually that particular question is slightly easy to do. Okay, but there is no general method. Okay.
Okay, sir. Then
I'll come to that.
I will ask in the later, sir. I will ask later.
Yes, let me solve one question related to Prim's algorithm.
Sure.
One question, sir.
Mm-hmm.
Sir, it is a Prim's algorithm can we apply this Prim's algorithm in directed graph also?
No. We need to apply it for undirected graph.
Okay.
Yes.
Sir, if there is a edge of same weight, then how we proceed?
No, you can pick any one of them. Okay.
So there are many questions like if we use the same weight edges are there, so how many ways we can find minimum spanning tree? Then how to?
Okay, I'll come to that. Let me solve one question. Okay. So you consider this graph.
Whatever can we use this for negative edges also?
Yes, you
negative
can.
Weight.
You can use. Okay, no issue. So this is 2, this is 3, this is, as you can see here, you have a negative weightage. Okay. This is A. Let's say this is C. This is from A to C. 1, 5, minus 2.
It is E.
Okay. Okay. I guess
E is repeated.
Yes. My bad. Yeah.
Yes.
Then this is F. This is, I guess, 6, 1. And what is the weight of this E comma F?
Minus 6.
Minus 6, right? Okay. So this is my graph, and as you can see, and one more thing you have to remember that you can apply Prim's algorithm to a connected graph. So this is a connected graph, right? So this is a connected undirected graph. Okay. That means I can apply Prim's algorithm. Okay. So first what I need to do, so here I have 1, 2, 3, 4, 5, 6. Okay, 6 vertices. So if I try to draw the maximal spanning tree for this graph, then I should get a graph of n minus 1 edges, that is 5 edges. Okay, so then what is my starting edge for this? If I apply Prim's algorithm, what will be my starting edge for this graph?
EF.
EF, sir.
EF, sir.
This
EF.
one. Correct.
Yes, sir.
Yes. So this has minimum
EF.
edge weight. Okay, that is minus 6. So I'll start with E comma F. Okay. So this is my E. This is my A. So now, the next thing is I have to go for the neighbors of this edge, right? EF. So what are the neighbors of EF?
DE.
EB. ED.
This is a neighbor. This A is a neighbor. B E is a neighbor, and E D is a neighbor, right? And B D F is a neighbor. Okay. So among all these edges, which has
BA
the
is not a neighbor.
Sorry?
BA is not a neighbor.
BA is not a neighbor. B is, is there any so why you think BA is a neighbor? Because there is no
We have taken D and F also.
B and
we are checking D and F. D and F also we have taken.
Because
so
there
we
is
are checking.
Hello, am I audible?
Yes, sir.
Yes, sir. Yes, sir. Yes, sir.
Yes, sir. Audible.
Yes. So as you can see, there is a direct edge from this this D to F, right?
Yes.
So it's a direct. So there is a direct edge connected to this A this edge, right? This edge is directly connected to EF, right? This edge DF is directly connected to EF. But if you see this edge BA, it's not directly connected to EF, right? Is it clear?
Oh, sir.
Sorry?
No, okay.
No, you are not audible.
Clear,
Like,
sir. Means
hello?
it's not clear, sir.
Yes, sir, yes, sir.
Yes.
No, half of your words. Hello? Am I audible?
Yes, sir.
Yes.
Yes, sir. You.
So see the
So
thing.
I was just saying means A and B. It is also connected to means you said B and F is directly connected to E and F.
Yeah, because see this is direct. So there is an intersection in that edge, right? This DF and EF,
Yes.
they
Okay.
intersect at F, right? And
Okay.
where this A, B, and EF intersect, there is no intersection, right?
No.
So then
Okay, I got it.
how B and BA and EF, they can't be neighbor, right? Okay, there is no intersection.
But it can be a neighbor of EA or EA then?
But I'm not talking about the neighbor of EA, right? Now I'm concerned about the neighbor of EF, right?
Okay, sir.
Yeah. So okay.
Got it. Now got it.
So the thing is, as you can see, this vertex. So I have started with the vertex EF. Sorry, the edge EF, and this EF has 4 neighbors. Okay. So among all the 4 neighbors, which has minimum weight?
-2 AE.
So this is -2, this is 5, this is 1, and this is 6, right? So the minimum age is basically sorry the minimum weight is of this age AE. Okay. AE. Now, as you can see, I can add this age. Okay. Now I can add this new age. Okay, this one. Right now I can add this new as AB, because this AB is related to the AB is a neighbor of AE, right? So now can you tell me which edge has minimum weight?
BD.
B
D.
-4.
No, but why? So the thing is, the problem is, okay, you are going to, so now what are the edges that are in my list? First you have to see. Okay.
AB. A to B.
AB.
AB is also 1 and ED is also 1, sir.
Okay, so basically I'm excluding something. So these edges are in my list. AB, okay.
EB.
EB.
ED.
ED.
And EF.
EF is already explored.
Already we have included.
EF is already explored, yes, sir.
Okay, so the next one is FD, right?
Sir, we should choose ED so we can eliminate DF.
Sir,
how come FD, sir?
FD won't be part of this iteration, sir.
Why?
Because we are only concerned about A and E, no, sir.
A and E only, no, sir.
So previously we have started. Okay, I guess.
Oh, okay.
Okay, let me. Okay, I guess I should write in little more clearly. Okay. Okay, so initially we have started with what?
E and F.
E and F, right?
Yes.
Now, what are the neighbors of E and F?
So it's EA.
FD.
FD.
AE.
BE.
BE.
E.
ED.
E.
And
FD.
Yes, sir.
FD, right? Right, correct?
Yes, sir.
Yes,
Now among these 4 edges, which has the minimum weight?
AE, sir.
AE, correct? Now AE. Okay, so now I can remove this A, correct?
Yes, sir.
Now in this list, so again, so anyone which is again in this list, I can I can add one more is right, because AB, this AB is also a neighbor of A, right?
Yes, sir.
Yes.
So then in this list I have one more S. Okay, correct?
Yes, sir.
So now among these four edges, which has the minimum weight?
AB and
ED.
AB and ED, right?
Yes. Yes.
So we can choose any one of them. Okay, so let me choose maybe AB, right? Let me choose AB, correct? So
Okay.
now I can remove this AB.
Yes, sir.
Right? Now what are the neighbors of AB? Because since I have included AB, so I have to go and I have to check what are the neighbors of AB.
Yeah.
What are the neighbors of AB?
BCs and BD, sir.
BC, BD.
Okay, so this is BC and
BD.
BD, right? Now tell me which of the following edges has which of the following has the minimum weight?
BD.
BD,
Yeah.
right? Correct.
So here we are not adding the total weight, right, sir?
Sorry.
Here we are not adding the total weight.
Yeah. So eventually, see, we're choosing the minimum weight, right?
Okay.
Every time we are choosing the minimum weight. So eventually you will get the what? You will get the minimum thing. Okay. Final weight, whatever. Yes. Okay. So now we have added BD, right? So we can remove BD. So once I included BD in my tree, then what are the neighbors of BD?
BC
and DC.
BC and
Sir,
CD.
BC is already there.
It's already there, sir.
Okay, BC is there. So then
CD.
I have to add CD, right?
Yeah.
Yes. Now among all the edges, which has the minimum weight?
EC. EC.
EC. EC.
No, sir. ED, sir. ED is a minimum.
ED.
Yeah.
But it forms a cycle.
But if I take ED, then that will form a cycle.
Okay.
Right?
Yeah.
Because if I join this S, then that will form a cycle. So I cannot include ED. Right?
Okay.
So the next question is among these four edges, which has the minimum weight?
BC.
BC. Can I join BC?
Yes, sir.
Yeah.
Yes.
Yes, sir.
Yes. I can join BC, right? Now this is the minimal spanning tree. This is the minimal spanning tree. Is it clear?
Yes, sir.
So as you can see, you can have two different minimal spanning tree. Okay. So if you see, so we had a situation where we had to choose in between A, B, and ED. Okay. So what we did, we have included AB instead of ED. Okay. So you can also include ED also instead of AB. Okay. If you include ED instead of AB, you will get another minimal spanning tree. Okay. And eventually they will give you the same thing. Yes.
To find.
Is it clear?
Yes, sir.
Okay.
Yes, sir.
Okay, so let's go to the Kruskal algorithm. Okay. So Kruskal algorithm also is more or less same, but okay. So here the idea is like little different. Okay, so instead of going to the neighbor smallest
Joining.
neighbor, okay, instead of going to the smallest neighbor, we have to go to the smallest edge. Okay. Okay, so let's take this example. The example we have taken in the beginning. Right, so this is my graph. 70, this is 6, I guess, this is 10, this is 18, this is 20, this is 8, right? Okay, so so this, now we are talking about Kruskal's algorithm. So okay, so in the Kruskal algorithm, so what we have to do, again we have to start with the smallest weight edge. Okay, so what is the smallest weight edge here?
1, 3.
1, 3. Okay. So this is 1, this is 4, this is 2, right? So I have to start with 1, 3. Okay. So next, what I have to do, instead of checking the neighbors of 1, 6, okay, so in Prim's algorithm, what we checked only the neighbors of 1, 6, right? So instead of checking the neighbors, what we have to check? We have to check all the remaining vertices. Okay, among all the remaining vertices, which has the minimum weight. Okay, can you tell me among all the, so we have included this one. So among all the remaining vertices, which has the minimum weight?
2, 4.
2, 4. Correct. So this is the, so among all the remaining edges, 2, 4 has the minimum. Okay. So now we have included 2, 4. Now, can you tell me among all the remaining edges?
0,
0, 1. Correct. Okay. So we have included 0, 1. Now, can you tell me among all the remaining edges?
1, 2.
1, 2. No, 0, 3.
No, 0, 3 will
0,
form
3
cycle.
will form cycle.
So 1, 2.
So the thing is, okay, no. So among all the remaining edges, so this one, and this one, right? So 0, 3 has minimum weight, correct? But I cannot include 0, 3 because if once I include 0, 3, okay, I'll get a cycle, right? So I cannot include 0, 3. So I have to exclude, now I have to exclude this edge. Okay, so now I'm left with 2 more edges. Okay, that is 3, 4 and 1, 2. And among these 2 edges, 1, 2 has the minimum
weight.
Okay. And as you can see, now we have completed this graph. Okay, so then this is the minimal spanning tree for this graph using Kruskal's algorithm. Okay.
So at the end of solving using both the algorithm, you will have the same trees as now.
No. You can have different.
Okay, because it seems to be the same.
No, for this case maybe it's same, but certainly this can be different. Okay. Okay, so let me take example.
Sir, which algorithm give the minimum spanning tree? Kruskal?
Both of them gives the minimal span.
Sir, if we take, you are saying we get different graph from both. So if we are getting different from both, then the minimum value will be different for both.
No. If you add, okay, so the total. If you add the edges of, if you add the weight of all the edges, okay, eventually you will get the same thing. Okay, the graphs may be different, but if you add the weights of all the edges, okay, of that tree, okay, you will get the same thing.
Okay, sir.
Okay, fine. Okay, so let me take one more example and let me do the Kruskal's algorithm for this one. Okay, let's take this is 0. 1, 2, 3, 4, 5, 6, 7. So this is now, this is my new graph. Okay, and the, let me mention the weight. Right. So now this is the graph. So can you tell me which edge has the minimum weight?
3, 4, and 2, 5.
Okay, so 0, 1. Let me mention the edges, then it will be more clearer to us. 3, 4, 5, 6, 7, 8. Right. So as you can see, this is 2, 5 has weight 1, and this is also has weight 1. Right. 3, 4, and 2, 1. Correct.
Yes, sir.
So what we can do, we can pick any one of them, right? So let's take 3, 4, right? So we have included this edge. Now among all the remaining edges, which has minimum weight?
3, 6.
1, 2, and
2,
5.
5.
2, 5, because see, we have included only, so initially we had 2 edges of minimum weight, 3, 4, and 2, 5. What we have done, we have included 3, 4. But so 2, 5 is now, 2, 5 is also available. Okay, so among all the remaining edges, now 2, 5 has minimum weight. Okay. So now we have included 2, 5. So now among all the remaining edges, which has minimum weight?
3,
0, 0, 1, and 3, 6.
1, 4, and 6.
Correct. So now this 0, 1 has weight 2, 1, 4 has weight 2, and 3, 6 has weight 2. Right. So next one, what we can do, we can add any one of them. Right. We can add any one of them. Let's say let's add 1, 4. Right. 1, 4. So we have added 1, 4. Okay. So next, which edge has minimum weight?
0, 1, and
0, 1, 3, 6.
0, 1, and 3, 6. Again, we can add any one of them. Let's take 0, 1. Okay. So we have added 0, 1. Then what is the next choice?
4, 5.
3, 6.
3, 6.
3, 6.
Because 3, 6 has weight 2. Right. So we have included 3, 6. Then what is the next choice?
4, 5, and 7, 8.
5, 7, 8.
4, 5. This one has weight 3, and this one has weight 3. So is there any problem if I include 4 and 5?
No, sir.
No, sir.
No problem. Correct. So I can include 4 and 5. Okay. So I have included 4 and 5. So I can discard it. So the next among all
7,
the
8.
remaining, correct, 7, 8. So now I can join 7 and 8. Okay. So now I can join 7 and 8. Okay. So then, so now we can discard 7 and 8. Sorry?
6 and 7 after that.
Sorry?
We can take 6 and 7 because for every 4 we will get a cycle.
4, 7 is the only that will not make a cycle, sir.
Okay, I'll come to that. So let me go one by one. So then among the remaining edges, which has the minimum weight?
1, 2, and 4, 7.
1, 2, and 4, 7, right? But if I take 1, 2, okay, so if I take 1, 2, then I will get a cycle,
Yes,
right?
sir.
Yes,
And
sir.
similarly, if I take 0, 3, then again I will get a cycle.
Yes,
Okay.
sir.
7,
So now,
6 we can do.
yeah, so I can discard 0, 3 and 1, 4. So again, now I'm
4,
left
7 we can no, sir.
4, 7.
Yes, sir.
Okay,
4,
sorry.
4, 7 we missed in between.
Yeah. So I can so I cannot take, so I have 3 edges of minimum weight, that is 1, 2, 0, 3 and 4, 7. Okay. So I cannot include 0, 3 and 2, 4 because if once I include one of them, then they will create a cycle. So I cannot include both of them. So that's why we have to add 4, 7 because
Yes,
4,
sir.
7 will not create cycle.
Yes, sir.
Okay. Now I guess we have completed the tree because okay, now we are left with 2 more edges, right? And
Yes, sir.
both of them have same weight, right?
Yes, sir.
Yes, sir.
6, 7, 5, 8.
6, 7, 5, 8. So if I include 6, 7, I will get a cycle.
Yes, sir.
Right?
Yes, sir.
And if I include 5, 8, then also I will get a cycle. Okay. So I cannot include both of them. Okay. So this is precisely this is this is again, this is not unique because you can see like many places you are getting
Same weights.
Okay, so if suppose if you choose some different order, then probably you can get some different graph. Okay, so let me come to the question like total possible spanning tree. So I guess one of you asked me like how many possible spanning tree is how many total number of possible spanning tree for this graph, right? This, let's say this is the graph. Correct?
Yes.
So as you can see, this how many, so this graph has how many edges?
8.
So
0, 1,
8.
2, 3, 4, 5, 6. Okay, I made
7, sir.
7, right?
Yes, sir.
Yeah. Yeah. So the thing is, if I remove any one of the edges from this side, right?
Yes.
And if I remove any one of the edges from this side, okay, then I will get a tree.
Yes.
Correct? Then spanning tree.
Yes.
Correct. Okay. So then how many, and one more thing, if I will not remove any edges from this side, okay, then it cannot be a tree.
Yes.
Yes, sir.
Because it's a cycle.
Yes.
So then somehow I have to remove one of the edges from this side, correct?
Yes.
And similar argument I can give for this right hand side, correct? Correct or no?
Yes, sir.
yes, sir.
So then I have to remove one edges from my left side, this cycle, and one edges from this right hand side. And how many ways we can do that?
Sir.
Sorry?
4 from left and
8.
4. 8.
8 way.
Not
8
8
ways.
ways. So in how many ways? In how many ways you can remove one edge from this side?
4.
2 ways.
4 ways, right?
4.
Not 4 ways.
Because you have four edges, right?
Yes, sir.
So
Yes, sir.
in 4 ways, in 4 ways, you can remove one of the edges from the left hand side.
Yes.
And this one, how many ways you can remove?
4 ways. 4 ways.
4 ways.
Right? And if you see both the tasks, okay, they are completely independent, right?
Yes, sir.
I can remove this one and I can remove this one. It's completely independent. So it doesn't matter what I'm so to remove some vertex from this side, it doesn't matter which vertex I am removing from the left hand side. Okay, so both the tasks, they are completely independent. That means how many total
4 into
number
4.
of correct?
Yes, sir.
64, 16, sir,
16.
16.
Sorry,
16.
6, not, yeah, 60. Is it clear?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay. So I guess, so now this part is clear, right? This minimal spanning tree.
Yes, sir. But
Yes,
sir,
sir,
I have a
very clear.
question.
Very
clear, sir.
Okay.
Sir, when to use Kruskal and when to use Prism?
No. There, I guess there is nothing like that. You can use both the algorithm. Okay, but I feel this Kruskal algorithm is slightly better. Okay, in terms of, I guess, complexity. I'm not sure, but see, when you run, so the thing is, you will run all this program in your computer. Okay, it's depend how much time this program is taking. Okay, so I'm not sure, but I think in terms of time, I guess this Kruskal algorithm is better. I'm not sure. Okay. In terms of complexity, I'm saying.
Sir, so to find the minimum number of spanning trees, we have to see in this way how to remove the edges which is connected.
Yeah, so that is what I explained, right? This both the algorithm, this Prim's algorithm and Kruskal algorithm.
Sir, if the graph is little more complicated, and we can see that in this case you have taken a graph and you have I think as a two quadrilateral, and you have removed one side by one side, and in this way you are permute and
no, that is I have in the beginning, actually I have like informed you that this whatever method I have used for this graph. Okay.
No, sir, not for this. I mean, if we want to count, like we have a complicated graph and we want to count how many minimum spanning trees possible, then should we have to approach in this way, or we have any formula or other
no, there is no such formula. Like you cannot, like, for any arbitrary graph, it's difficult for you to find the minimal total number of minimal spanning, different minimal spanning.
Okay, sir.
So particularly for this graph, it is easy. Okay, that's why I've used this method. Okay, I cannot.
For a graph, we are able to have only one minimum spanning tree, no, sir?
No, actually, you can have multiple minimal spanning.
I think in lecture it's mentioned that we will have only one minimum spanning tree, but we will have many spanning trees, but not minimum. Minimum is only one, it seems. That's what I want to make it clear.
No, sir. The graph
minimal value will be minimum value will be
for a weighted graph. Okay, for a weighted graph, the total value, whatever this minimum value, they are basically same. Okay. So for different, if you get also different graph, minimum spanning graph, the total weight of all this graph will be same.
Same. Okay.
But the graph, they can be different.
Okay. So we will have a different number of spanning trees for a graph.
Yeah. So for example, if you take this graph, okay, this is a graph, right?
Yes, sir.
A, B, C, and let me put some weight. 1, 1, 1. Right. So the minimum spanning tree is this can be a minimal spanning
tree. An L shape is also one.
Right. This can be also a minimal spanning tree.
Yes.
Okay. This can be is also a minimal spanning tree, right? Okay. But as you see, that may be different things, different graphs. But eventually, if you add, so here, if you add the total weight of all the edges, here you will get what? 2, right? Here also you will get 2.
2.
Here you will get 2. Okay. For different minimal spanning tree, okay, the total weight will be same. Okay.
Same.
But the graphs, they can be different.
Okay, sir. Clear, sir. Thank you, sir.
Yes.
Sir, these trees will be isomorph to each other, right? I mean, whatever minimal spanning tree we
No,
get.
we are not going to isomorphism. Okay. So there, but the thing is, if you see in terms of graph, they're slightly different. Don't go to the thing that that is not in the syllabus. See, isomorphism is something different thing and slightly complicated.
Okay, sir.
Sir, if we want to match the one of the 4 options, then see in the previous example what you explained, suppose if there are 2 edges with same weight, we can go for any one of the edge.
Correct. Yes.
If it does not form a cycle. Suppose if it is not there in the option, then again we have to go back and do it again, sir. Is it that procedure or?
Yes, correct. So the thing is, yeah. So the thing is, okay. So again, also like so if you have a bunch of option, I guess you by simply by just looking at that option and by looking at the original, probably you can decide whether that
whether it is whether there is a or not.
Yes. Yes.
Okay. Okay. So, okay, that's why, sir. So by means of practice, we can get it.
Yes, correct. So I guess like most of if you solve few problems, like after that, I guess you don't have to draw the graph. Just simply by looking at the original graph and the graph that is given in the option. Okay. Simply just by looking at both the graphs, you can tell that whether this is a minimal spanning tree or not.
Otherwise, it takes a lot of time, no, sir.
Yes. Otherwise, if you like, so the thing is, okay, so as I said, like this finding minimal spanning tree is little bit easier. Okay, but
yes,
if you
yes, this is easy, sir, when compared to other concepts.
Yeah, so if you do this, if you complete, so suppose you have a graph with some 10 vertices. Okay, so if you apply this, let's say Floyd-Warshall algorithm, then probably it might take more than half an hour or maybe 45 minutes. Okay.
Yes, sir.
Yes. But finding minimal spanning tree, it should not take much time. It's pretty easy. Okay.
Thank you, sir.
Yeah.
Floyd-Warshall is taking too much time, sir.
Yes, correct.
Sir, can you explain the Warshall and Floyd-Warshall algorithm?
Yeah, I'll come to that.
Basically, the
Yes, sure. I'll come to that. Okay. Let me actually, so the thing is, okay, so I have to come to that slide. As I said, so if you go and check this solve with a slide, okay, so basically there actually we have basically solved all the activity questions. Okay, so yeah, so all the questions related to this Bellman-Ford algorithm and this Floyd-Warshall algorithm we have solved in that slide. Okay.
So that implies
just one saying what sir said.
Sorry?
I was confused. What sir said means there was one thing that sir said. I was a bit confused with that. When he was calculating that the edge, he said that after once we visit every edge, we will update the value of that edge once we complete that cycle. So I'm not getting what that actually means.
Okay, let me
the only thing that I want to understand.
Let me share the screen. Okay. Whether the screen is visible to you?
Yes, sir.
Yeah. Okay. Yeah. So basically, let me start with this Bellman-Ford algorithm. Okay. I'll start with the example, so it will be clearer to you once you see one example. Okay. So the thing is, what you need to do, you need to before that one question. So Bellman-Ford is a single source shortest path or all pairs shortest path?
Yes, sir, single source, sir.
So
single source shortest path.
Yeah. So single source means, so if the graph is so if the algorithm is single source, then you have to start with some vertex, right?
Yes, sir.
So you must have a source vertex, right?
Yes, sir.
So you must have a source vertex, right? So in this case, you have a source vertex which is 0, right? Suppose for this graph, whatever graph is given here. Okay, so for this graph, the source vertex is 0. What do we want to do? We want to compute. So using this Bellman-Ford algorithm, we want to compute the shortest path from 0 to all other vertices. Okay. So, sorry, any doubt?
So carry on. No, sir. No, sir.
Okay.
I just said okay.
Yeah. So, so initially, so we'll start with 0. Okay. So initial thing is we are starting with 0 and we don't have any other information. Okay. So initially we don't know the value of the shortest path from 0 to any other vertices. Okay. Initially we don't know. Okay. So for that we will define the shortest path to be infinity, or to all the other vertices. And since we are starting with 0, okay, so that's why the initial the shortest path from 0 to 0 is basically 0. Okay, correct. So still now it's clear how actually we are starting with the algorithm.
Yes, sir.
So
Yes,
now,
sir.
Yes. Hello.
Sir, repeat once again, sir.
Sorry.
So again, so what I am saying, so this is a single source shortest path, right? So since this is a single source shortest path, what we have to do, we have to start with a, so first we have to fix a vertex, okay? Because if we don't know from which vertex we are going to start, then there is no point, we cannot do anything. So we have to fix a vertex. So we have to fix a source vertex, right? We have to fix a source vertex. Okay, so in this case, the source vertex is 0. And what we need to, what basically we're trying here, using this Bellman-Ford algorithm, we are trying to find the shortest path to all other vertices. Correct? That is what we are trying to do using this Bellman-Ford algorithm. Okay, so since initially we are in this vertex, okay, and we don't have any information about the shortest path to any other vertices. Okay, so that's why we will define this to be infinity, 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 and infinity. We don't know what is the shortest path from 0 to 7 or 0 to any other vertices. Initially we don't know. Okay, that's why that is how we define this algorithm. Okay, and the shortest path from 0 to 0 is basically 0. Okay, so that is what I have written. Okay, correct. Yes. So next, so now I have 0. Okay, now I have 0. Okay, so what I have to do now, once I reach in the 0, okay, I have to explore its neighbor vertices. Okay, what are the neighbor vertices of vertices of 0?
1, 4, and
7.
So there is a edge from 0 to 1. Okay, and there is a edge from 0 to
4.
7, and there is another edge from 0 to 4. Okay, so now I know, okay, there is a edge from 0 to 4 whose weight is 4, correct? And there is a edge from 0 to 7 whose weight is 6, right? And there is a edge from 0 to 1 whose weight is 10. So initially I did not have any information about, so as you can see, initially I didn't have any information about the weight of the path from 0 to 7, 0 to 4, 0 to 1, and 0 to yeah, so that's all. So now, but now I have information of the weight of this edge, 0 to 7, 0 to 4, and 0 to 1. So what I will do now, I will update it in this table. Okay, so in the next column, what I will write, this is 0. Okay, and now I know the length. Now I know weight of this path 0 to 1, which is
10.
10, right? But I don't know the length of path from 0 to 2, right?
Yes, sir.
I don't have any information till now. So this is still infinity.
Infinity.
Okay. So the next thing is 3, 0 to 3. Again, I don't have
infinity, sir.
That is also I don't know. Then also now 4. But
It's
I
4,
have
sir.
but now I have this information 4. Okay.
It's 4. Yes, sir.
And the next thing is I guess 5, which is also infinity. Okay. 6 also infinity. Okay.
And 6.
And for 7, I know it's 6.
6.
Right? Okay, so this is the next step. As you can see, this is the next step. Okay. So now from 0, so initially I was here 0. Okay. Now I have reached to 7. I have reached to 1, and I have reached to 4, right? Because that is what I have updated here. Okay. So next, what we need to do, we need to explore the adjacent vertices of 7, 1, and 4, right? That is what our next task is. Okay. So as you can see, I cannot go anywhere from 4, right? There is no vertices which is going from 4. Is it clear?
Yes, sir.
Because all the vertices are coming towards 4.
In vertex. All are in vertex.
Correct. Okay, please. Okay, so please mute yourself. So the next thing is what I can do. I can from 7 I can come to 6, right? From 7 I can come to 6, and from 1 I can come to 2, right? 2. So what I can do now? So now I have few more information, right?
Yes, sir.
So now I know the distance between 0 to 2, right? I know the distance between 0 to 6, right? So I need to update it, right? So this is 0, then 1 it's 10, right? And what I can write here?
11.
11.
Yeah, correct. And what I can write in place of 3? Nothing, right? Infinity. And in place of 4, it's 4.
4, okay.
Because see, it was there from the previous table. We have written here 4.
Okay.
And in this thing, so here actually we are not getting any new information about 4. Okay. So,
sir, from 3, how it is infinity, sir?
3, still now we have not reached to 3, right?
Oh, okay. That's right.
Because we have still now this is infinity, this is infinity, because still now we have not reached here.
Yeah.
Okay. So we have reached till 6 and 2. Okay. And we have already explored the 7 and 1. Okay. So then what is what will be this value? 5?
Infinity, sir.
Then what about the value of this one? 6?
4.
6 plus minus 2, this is 4. Okay. And then this 7?
6.
6, sir.
7, 6. Okay. So the 7, so once, okay, sorry. So 7, I will get 6. Okay. So now this is my new table, right? Correct?
Correct, sir.
So here, if you see, hello?
Yes, sir.
Yeah. So here, if you see, we have explored 2 more edges, right? So here we have explored 2 and 6, right? So this is my new table, correct? This is my new table. Okay, now here we have explored 2 and 6, right? So initially, if you see, initially I so as you can see, I can come 0 to 1 and 1 to 2. Okay, and from 2 where I can go
5.
I can go to
5.
5, sir.
I can go to 5.
Also
I can go to
7.
7, right?
Right.
So if you see, if I come to 2, if I from 0 to 1 and then I come to 2 and then I come to 7, what will be the total weight of this path?
1.
8 plus
19,
5.
sir. 19.
9, yeah.
Not 19.
0,
Minus,
1.
minus.
minus 3, sir.
Yeah.
This is 3. This is 3.
Sorry, 3, sir.
This is 11 minus 8, which is 3.
3, sir.
Okay. And
Oh.
if you see the previous, like here in the table, what we have written here,
6.
what is the
6.
minimum path?
6.
6.
6, right? But so now what we are getting a new path through 2, because we have already explored 2. We are getting a new path, okay, whose weight is 3, right? So now what I can do, instead of writing 6 here, I can write 3, correct?
Yes, sir.
Yes,
Correct.
sir.
So then okay, so now we have updated this. So again, this will be 0, okay, and from 0 to 1 I'll get 10, okay, and from 0 to 2 what I will get now?
11. 11, sir.
11, okay,
11 only.
yes, and what I can get from 0 to 3?
8, sir.
Why?
Infinity.
Say infinity. Still it is infinity.
Oh,
Not
yes, sir.
excluded.
No, sir. From 6, we are able to go to 3,
Correct.
no, sir.
Correct. Yes. So the thing is, you can actually from 6.
Oh, 0 to 7, 7 to 6.
Yeah. So you can.
Yeah, 0 to 7, 7 to 6, 6 to 3.
Correct. 0 to 7, 7 to 6, and 6 to 3. Okay.
So 4,
then it is
4
4,
plus
sir.
4, 8, sir.
Correct.
8.
Okay. What about 4? It's
4
4.
same.
It's 4
sir.
same.
4.
Correct. Then what about 5?
1, sir.
1.
It's 1.
You are saying 5.
2 to 5, sir.
0 to 1, 1
Sir,
to
2
2,
to
2
5,
to
sir.
5.
0 to 1,
1 to 2, 2
No,
to
10.
5.
2 to
10,
5.
11.
11
sir.
minus
11
1.
minus 10.
Sir, 11
It's
minus
1.
10, sir. It's 1.
11 minus 10. It's
It's
4.
1.
Yes.
1.
1, 1, sir.
Correct. Okay. Then what
4.
about
4, sir.
It's also
6?
6, no, sir. 6 is
Sorry?
1, sir. 6,
Sorry?
sir. 6.
Same,
6.
same, no, sir. 4
Yes.
only.
4 only, sir.
Yeah.
Yes, correct. So then we'll get this. Then basically we'll get this column, right?
Why 6 to 6 will be 4?
Sorry.
We can move from 0 to 2. Why 6 will be 4? Because we can move from 0 to directly that, and then
Sir, there is a way from 0 to 1 to 2, 2 to 7, 7 to 6.
2 to 7,
7 to 6.
7 to 6. Yeah, that is possible. Yeah, that will update it later. Okay, now we are actually checking. So basically what we have done here. Okay, so we are basically explored these 2 new edges, right? 2 and 6, correct?
Yes, sir.
Yes, sir.
So basically we are checking how many. So what are the new edges? What are the edges that basically coming out of these 2 edges? Okay, so
3
this
and
edge,
5.
this edge is coming out of 2. Okay, this edge is coming out of 2. Okay, and this edge is coming out of 2. Okay, So next actually we'll go and see what are
3 and 5, sir.
Yes, correct. Yeah, so no. So the thing is 3 and 5, sorry, you are saying 3 and 5.
No, next I'm asking we have to look into other vertex.
Yeah, so the thing is, see, so here if you see here actually here we have explored these two edges, right? We have reached to these two edges. So we are checking actually all the edges, okay, that is coming out of these two vertices. Okay, so this is edge, this is a edge, and this is one more edge, right? And we are actually updating the information using these three edges. Okay, so as someone said that why we are considering this path. Okay, we can consider why we are considering this path. We can consider this one, and this one. Okay, that is what you are saying, right?
Yes.
Yeah, we'll come to that in the next step. We'll come to that. Yes. Hello.
If that is so, then why we have updated that value of 6?
Sorry.
Because we haven't explored the 6. We haven't explored the 6 yet. We have only explored the 7. And if the same goes for, means are we just calculating the edges which are outgoing, and then at the later stage we are updating the values?
Yeah, so here actually we reached here, right? 2 and 6, right? So if you see here, we have reached 2 and 6, right?
Yes.
We have reached 2, 6, and 4, right? So once we reach 2, 6, and 4, and in the next step, actually, we are updating this. Okay. So this.
Okay. I now got it. What sir said.
So what actually I am doing? I am writing the next step here itself. Okay. So if you see, this is actually the next step. Okay, and I am updating it in this table itself. Okay. Is it clear or still confusing?
Clear.
Okay.
Sir, I got it. What it meant by what sir said. What was the main confusion? I got it. We have to later update the values. First, we have what neighboring places that we can visit.
Okay, and one of the most crucial thing is always remember that a shortest path will extend to another shortest path. Okay, so that is really crucial, because since we got one shortest path from here to here. Okay, so next thing what you need to do, you need to check whether we can get any more shortest path using this path. Okay. Okay, so
sir, one question, sir. So we have to look the shortest part, right?
Yes, that is what we have.
That means from 0 to 7, 7 to 6, right? Instead of 0 to 1, 1 to 2, 2 to 7, 7 to 6.
Yes, that is basically the next step. Okay. So in the next step, what if you come to the next step? Okay. So this is after performing 3 steps. So after performing 3 or fourth, third step, I'm getting this column. Okay, so after performing third step, we are getting this column. Okay, so the next step is, as you have already mentioned, so the next step, what we need to do, we need to update. So as you can see, I can come to here, and I can come to here, then I can come to here. So if I add, then what I will get? I will get, and what is the total length of this path? What is the total weight of this path?
Sir, 10, sir,
1.
14, 14.
1.
Sir, 14 minus
length or weight,
sir, 12, sir. Sir, 12, sir.
1. It is -8.
-8. It's 1, sir.
Sir, isn't it already updated? It's 3 right now, right? So 10 plus 1 plus 3 is equal to for total 14.
No.
14 minus 2 is
1.
No, no. So the thing is, if you see, we have not we have updated to the path, this path from 0 to 7. Okay, still now we have not updated this path. Okay, from 0 to 6. Okay, this is still 4, right? This is still 4. 6 plus minus 2, which is 4. Now, instead of that, if I consider this path, okay, instead of this path, this direct path, okay, which is 4, but if I consider this twisted path, I'll get 1, right? And as you can see, 1 is less than 4. So then I have to, instead of 4 here, I have to update 1. Okay, is it clear why actually we are updating now? We are updating 1 here because we are getting one more path which is shorter, which is the weight of that path is lower than the previous path. Okay, so once I have this path, so since we are getting this path which has lower weight, now we need to explore something more using this path. Okay, so
sir, in this case for 0 to sir, we have also one another path now which has little bit more weight, like 0 to 5, because 5 is also going to 6. So 0 to 5 is 1, and from 5 to 6 is 1 plus 1 2. So we are taking minimum of these two paths, right, sir?
Yeah, that is what we need to do. We need to find the minimum weight path, right?
Okay, so we have to take each and every possibility of for updating any vertex. I mean, 6 is updating in here 2 ways, and then we are taking which is minimum.
Yes, that is actually the most in some sense tricky part. Okay, you have to actually consider all the possible paths and you have to choose the minimum. So that is
I have a question, sir. So we are going by ascending order, right? I mean, the shortest part, like 0 to 7 to 6, right?
Yes.
Then 0 to 1, 0 to 1, 1 to 2, 2 to 7, 7 to 6, right?
Yes.
Then we will consider 0 to 1, 1 to 2, 2 to 5, 5 to 6. Isn't it?
2 to 5, 5 to 6, correct. Yes. Yes.
Okay, sir.
So as I said, like, see, previously, see here, so here, so if you see this path, okay, this was my shortest path to 7, right?
Yes.
This was my shortest path to 7, right? So then obviously the next choice is I have to see what are the edges that is going from 7 to some other edge, right? So if I include this edge, then obviously it will give me a shortest path to
6
from 0 to 6, right? So obviously now, since I got a shortest path to 7, then I have to go and check what are the edges that are going from 6, right? Sorry, what are the edges that are going from coming out of 7? So we have only one edge, right? This one, and the weight of this edge is -2, and after adding 10 plus 1 minus 8 and 2, we are getting what? 1. Okay, so the next thing is what you need to do. Now we have 6. Now you reached 6, right?
Yes, sir.
So then you need to see what are the edges that is coming out of 6. Which edge is coming out of 6?
3.
Sir, what about going towards 6, sir?
No,
sir,
because
we have another options, right? I told you, like 0 to 1, 1 to 2, 2 to 5, and 5 to 6.
0 to 1, 1 to 2, 2 to 3,
2 to 5, sir.
2 to
0 to 1, 1 to 2, 2 to 5, and 5 to 6.
This path is not minimum, na? It has the cost of 2, and we have already seen cost 1 as we move from 0 to 7 and.
Okay, got it.
Yes.
Got it.
So because see, we have, as I said, so if you have a shortest path, okay, this is a shortest path to 7, okay. So then if you are searching for a shortest path to 6, okay, then obviously you have to include this in that new path, right? because this is the shortest path to 7, and you have a edge from 7 to 6. Okay, you don't have any other edges from 7 to anyone else. Okay, so then
got it, sir. That means until and unless we are finding the shortest path, we are trying to find, we are exploring more way to going towards the shortest path, isn't it?
Yes, correct. So now if you consider this path, then you will get the weight, you will get a new weight, which is 1, right? So now you have reached to 6, right? Now you have reached to 6 using a shortest path, correct? So next, what you need to do?
6 to 3.
Next, you need to see how many edges that are coming out of 6, right?
6 to 3.
So there is only one edge which is coming out of 6. That is what? 3.
6 to 3, sir.
Right? And if I compute the total length of this path, what I will get?
5.
5. Right? And previously, what was the edge of this path?
8.
8, right? And now we are getting 5, which is less than 5 is less than 8. So we will consider 5. Okay. So then next, what we need to do?
From 3, what are the edges going out?
What are the edges going out? Right?
Yes, sir.
What are the edges going out?
3 to 2.
So 3 to 2.
And 3
to 4.
4. But if I take this as 3 to 2, okay, if I take this as 3 to 2, okay, then what will be the length of that path?
20.
20, sir.
What I am doing here, now I am coming to 7, 7 to 6, 6 to 3, 3 to 2. What will be the total length of this path?
11.
11.
11, yes, sir.
Sure, 11. 10 plus 1.
Yes, sir.
Minus 8, which is 3. Then minus 2.
Minus 2, sir.
1.
Which is 1.
1.
Then it's 4.
5.
5 plus 20, which is 25.
25.
But previously,
25.
what is previously? We had 11, right? Correct? Previously we had 11. Now we are getting 25. So we don't need to update this one, right? And what is the next path? There is a path from 3 to 4. Then what is the length of this path now? This new path?
2, sir.
So now we have updated this one. So now I'm talking about this path. This one, this one, this one.
6 to 3 and 3 to 4.
Right. So
yes,
what is this now? This is
2.
2, right? So previously we had 4, right?
Correct.
And now we are getting something so a number which is less than 4, that is 2. So I will update it. Correct?
Yes, sir.
So now actually, if you see, I cannot go anywhere else. Okay. If you see, I am with 4. Right? Right?
Yes,
and I cannot go anywhere from 4. Okay. And this, if I'll come to 2, okay, then this is not a shortest path, right? If this is not a shortest path, then it's not going to extend any shortest path. So if this path is not shortest path, if I'll extend it, then I'm not going to get any shortest path. Okay. So then I have to stop here. Okay. So again, what basically I'm trying to say. So once you get a shortest path, okay, try to explore that what you can get from that shortest path, because once we get this path, okay, after that actually we have tried to explore more and more using that path. Okay. From 7 we reached 6, and once we reached 6, then we have explored 3. Okay, and once we reach 3, we have explored 2 and 4. But by exploring 2, we didn't get anything new. Okay, so this path is pointless to explore. Okay, so then and once we reach 4, we cannot go anywhere. Okay, so that is actually the main idea. So the main thing is this one, this path. The main idea is to get this path. Once you get this path, after that everything you can explore it. You can get all other paths. Okay. Okay, so this
is similar to DFS. We are calculating we are extending the shortest path, so we are calculating a depth. So can we say that this is similar to DFS also?
Sorry, this is similar to
a DFS tree.
No. That is not similar to DFS tree. This is see, if you see all the algorithm, basically more or less we are doing the same thing. Okay, so more or less we are doing the same thing. So if you see the Prim's algorithm, okay, so if you see the Prim's algorithm, what basically we have done here. So we have a path. Okay, we are starting with the smallest one. Okay, so then what we are going, after that what we are doing, we are going for its neighbor. Okay, how we can extend this part? We can extend this smallest path to one more smallest path. Okay, so that is what basically we are doing here. So initially first we have somehow observed that this is the smallest path to 7. Okay, this is the smallest path to 7, and once we know that this is the smallest path to 7, okay, then what we have done, we have explored the neighbors of 7. So the first, so in this case there is only one neighbors of 7, which is 6. Okay, so after that we got a shortest path to 6, right? Then what we have done here, we have explored the neighbors of 6, and there is only one neighbors of 6, that is 3, right? Then we got a shortest path to 3, and then we have explored the neighbors of 3, that is 2 and 4. But the problem is this new path from 3 to T, this is sort of pointless. Okay, if we are adding this path, then we are not getting a shortest path to 2. So that's why we have discarded this one. But this path is very useful. So using this path, we are getting a shortest path to 4. And from 4, we cannot go to anywhere. So we are stuck here. Okay, is it clear?
Yes, sir.
Okay, fine. Okay, so again, I'll suggest you can, okay, so you can go through this Floyd Warshel algorithm. So again, we have explained it here. Okay, so you can go through it. And
sir, one question, sir.
Yes,
sir. Instead of sir 20, if it would be sir minus 20, then
if it would be minus 20, right?
Yes, instead of 20, it would be minus 20.
Minus 20.
Then we must choose this part, right?
Correct, because in the end, what we are getting, you try to add what you are getting. If you add, what you will see, what you are getting, 10,
5 minus 15
plus 1
minus
minus
15.
Then obviously you have 50, 11 here, right? So you have 11 here, right? If you get minus 15, then certainly minus 15 is less than 11. So then you have to update minus 15. Okay, minus 15.
Okay,
so when we updated 5.
Sorry, hello?
Updated 5.
I can't complete for 2. Yeah, we'll again go for 5, no, sir? When 2 becomes minus 15.
Yeah, so then certainly you have to update 2, and obviously you have to go to -5. Yeah, 5 also. Yeah.
Okay.
Then probably you have to do maybe one more step, or maybe then from 5 maybe probably you have to go and see to 4 also. Okay.
4 and 6.
Yeah.
Okay.
Yeah. So then probably you have to do 2 more steps. But certainly you will get a shorter path to 2. That is for sure. If you will change this to 20 to -20, then certainly you will get a shorter path to 2.
Okay, sir.
Why, sir? I asked because in exam time we have a very less time. If we start creating this kind of table,
so
directly if we would have answer, for example, -15. If we know the answer, then we could have write easily.
That is, I agree, but most likely will not give you this kind of question in exam. Okay, so because this exam is sort of 1 hour and 1.5 hours. So if I will give this question, then certainly I have to give you 20 minutes for this question. Right?
Yes, sir.
So I cannot give you 5 minutes for this question, right? So then it will take almost 1/3 time of your exam. So then
minimum half an hour it will take, sir.
So then, yeah, so then I cannot give you more questions, right? So that is the problem.
Sir, but in activity, they used to ask SP 05, 04.
Activity questions very lengthy, sir.
No,
Yes,
activity question is
how to
different.
calculate that one and also.
No, activity question is different. Okay, so there you have time. Okay, so in exam you have fixed
No,
time.
actually, I'm asking, sir, how to do that? SP0, SP1, 2, 3.
SP3, 5.
Okay, so that is what I am saying, right? If you go through this slide, okay, so I'll suggest you to go through the slide. If you have doubt, then probably you can ask tomorrow. Okay, basically
okay, solve with us, sir.
Yes, basically tomorrow Vicky is going to discuss this slide. Okay, so again you will see like this question. If you can see, like we have basically solved all the activity question related to this Floyd-Warshall algorithm.
Okay, sir.
Okay, so again, like if I can explain again, it will take maybe more than half an hour to explain.
Okay, sir.
Yeah. So any other doubt apart from?
Yes, sir. I'm having doubts in activity questions, sir.
Yes.
11.5, first one.
Sorry, 11.5,
sir. The first question, sir.
Okay, so okay, so this is basically what so in the ministry gave flood warning to the cities A, B, C, D, E, which are very near to the foothills of Himalaya, and at 0 time the city B was completely flooded in the graph city. Then at which time, at what time will city G start flooding? So okay, so again, mostly you have to do the same thing, right?
Yes, sir.
So you have to find
I got 14, sir, but the answer is
not 14. It cannot be. So I guess you have to. So there is a path, right, from B to C, right?
Yes, sir.
1, C to A, 2,
3,
3, then
A to D, sir. 4.
No, not A to D.
F, F to G, sir.
A to F, F to G.
Yes, sir.
Okay.
8.
Okay, sir.
B to C, C to A to F, F to G.
Yes. So now, okay, so now you know Prim's algorithm, right?
Yes, sir.
Now you can apply it, right, to solve this question.
Okay, sir.
You can so even you can go with the normal method. Okay. Otherwise, if you want to do it little quickly, then probably you can apply this Prim's algorithm or maybe Kruskal algorithm.
Okay, so even for the third question, they're asking for at what time will all the cities be flooded? So from B, we have to. The third one, sir.
Yes, yes.
Use diax, no, sir.
Sorry.
Which is the shortest path? We have to choose that one, sir.
Yes, yes, yes. So you have to choose a shortest path. So basically, what in the question number 1, they asked? They asked when the city G will start
flooding.
So basically, what you need to do, you need to find a shortest path from B to G. Right?
B to G, yes, sir. For the first question.
Yes, for the first question.
Sorry.
For the last one, sir.
Question.
To use diax, no, sir.
Sorry.
Can you please?
For the last one.
That's pronounced, sir.
Hello.
Hello, sir. Sir, we have to use diaster, no, sir.
Yeah, you can use diasters also.
So, sir, when we use Prim's algorithm, then we will get the then we will get the minimal spanning tree, and then we choose another edge from that vertex to, I mean, other, or how we can know when that city will burn.
No, so okay, so the thing is, you have to carefully use the Prim's algorithm. Okay,
so that we can see the vertex.
Yes, because see, Prim's algorithm, why I said actually Prim's algorithm. So one of the main reasons, obviously you cannot use Prim's algorithm everywhere. Okay, because here actually the edge, this BC has the lowest, like if you see, BC has the lowest weight, right? BC has the lowest weight.
Yes, sir.
Right. So you can start.
Excuse, can you please share the question on screen?
Okay, so just a minute. Okay, I guess I have this question here. I guess this one, right?
Yes, sir.
So why actually I have said Prim's algorithm? Okay, so suppose so if I change this question to something else, okay, so suppose if I change the weight of this, if I change the weight of this to 1 to maybe say 15, okay, then actually you cannot use Prim's algorithm. Okay, then you are in trouble. Okay.
Oh, sir, actually I'm asking how to approach the third question, sir. From where to where, which is the...
No. One student actually asked like why you think you can apply Prim's algorithm. Okay, so the standard way is to basically to use the Dijkstra algorithm. Okay, so the standard way is basically to use the Dijkstra algorithm. Okay, so so my suggestion, okay, even if you try to use Prim's algorithm also you can do. So the one of the main reason is basically the length of this is actually minimum. Okay, if you see all the edges, okay, weight of all the edges, this has minimum. Even also AD has minimum and EF has also minimum. But if you choose BC, then actually you can get a minimal spanning tree. Okay, so using that, most likely you will get this path. Okay, so if you try to extend
AFG.
Yeah, so probably you can get this one.
Yes, sir. Yes, sir.
Yeah, so that is what my plan, like that is what I thought. Okay, that's why I said okay, you can use. But again, I'm saying if I change this to 1 to maybe 15, then it's not possible.
No, sir, but the question is all the cities should be flooded, sir. Then we should cover all the vertex. No,
I'm again, I'm not answering question number 3.
Okay.
Okay, I'm not answering question number 3.
the same
Okay.
issue.
Yeah.
Now you have already shown us the minimal spanning tree. So can we now answer that also the total, I mean, when the all cities will be flooded in this way? Because we have all, you know, all the connected tree. I mean, everybody is connected. So is not the total cost will be the time when every city will be flooded?
Sorry, you are asking me, or I thought you were giving the solution of this question.
I'm asking you, sir. I'm asking you.
So what is your question?
So if now we are you apply Prim's algorithm, and we have got the this minimal cost spanning tree. So the total cost, I mean total time of the flooded of every city will be that minimal cost.
No, I don't think so, because no. So the problem is, okay, so the minimal spanning tree, you can have something like this, right? So in a minimal spanning tree, you have something like this. Okay. So then probably in this type of case, maybe you are in trouble. Okay. If your minimal spanning tree maybe probably like this, then probably you can get. So you have to take the maximum of this. I'm not sure for this question whether to get the answer of question number 3, okay, whether we can apply Prim's algorithm or okay, can you mute? I'm actually getting a lot of noises from. Okay, so let's do it. Okay, let's apply Prim's algorithm. Sorry, not Prim's algorithm. This Dijkstra algorithm to this question. Okay, so what actually we are doing? Okay, so what we want? We want we want to find the minimum time. What is
For all the
what
cities to be
city
flooded.
will be flooded? Okay, so so we are starting with this vertex B, right?
Yes, sir.
So this is initially the time is 0, right?
Yes, sir.
Okay. So next, what are the edges? Sorry, what are the vertices connected to this B?
C, A, G.
C, A, G. So what is this? What is the weight of this graph? So how much time it will take for me to reach B to C?
1 minute.
1, right? And how much time it will take for me to reach B to A? It's 4, right? And how much
14.
time it will take? It's 14, right? So now what I have to do? So
From
then
C to A, sir.
so yeah, so now in which vertex I will reach first? From B. See, if I'm starting from the vertex B, then to which vertex I will reach first?
To A, sir.
How?
B to C and C to A, no, sir.
So for B to A, it will take 4 minutes, right? And
no, I'm telling B to C and C to A.
No. Now I'm concerned about the
only B vertex.
Only these three vertices A,
Okay.
C, G. Okay. So from B, I will reach to C first. Right?
Yes.
Right. So and now from C to, now I have to check the neighbors of C. From C to A, how much time it will take? It's 2 minutes.
Yeah.
Right. And initially I have 1 minute here.
So 3 minutes.
So this is 3 minutes. So, but it is written it's 4 minutes. So now I can update it, right? So I can update it to 3 minutes, right? So next, what I need to do, I need to update the neighbors of A, right? What are the neighbors of A?
D, F, E. And F, E.
This one, and this one, right?
Yes, sir.
D, F, E. So how much time it will take for me to reach A to D?
4.
1.
It is totally 4.
Yeah.
4.
So this is 1, and from B to A, it will take 3 minutes, right? So totally 4. Okay. And similarly, A to E, it will take 10 minutes. A to E, it will take 10 minutes. And from B to A, it will take 3 minutes. So total 13 minutes, right?
Yes.
B to F also 4 minutes, sir.
Yes. B and A to F?
4 minutes.
4 minutes. Okay. So then what next? What I should do?
We should explore D. What are the vertices connected to D, sir?
Sorry. So,
no, I'm telling that next we have to move to the other vertices like D or E.
So next, what I need to do? So within 4 minutes, I will reach F, right? So then from F, what are the neighbors of? See, I have the neighbors of D, right? Sorry, if you see the neighbors of D, what are the neighbors of D? F.
A and F.
A and F.
A, no, already I have explored B, C, A, B, C, A,
so
right?
Only F.
F only.
Now we have only F. And if you see, I'm get from D to F, it will take 5 minutes.
Yeah.
Okay. Total
so
9
it becomes
minutes.
9. But already we are in 4.
But we have already reached in 4.
Yeah.
Okay. So
yes,
then we don't have to update it. Okay. So now this is 4. F is also 4. D is also 4. Right?
Yes,
So the next thing is now this G is 14. Now we have to explore the neighbors of F. Right? From F to G, how much time it will take? 4 minutes. Then 4 plus 4, this is
8.
8 minutes.
8 minutes, right? Right? And from
yes,
G to E, how much time it will take?
1
minute. And previously it was 13 minutes. Okay. So now, if I add 9 minutes. So as you can see, now I have covered all the vertices. Right?
Correct.
I have covered all the vertices within 9 minutes.
Okay, sir.
Is it clear? Like basically what we are doing, we are trying to see so we are exploring all the shortest path from this verse. So as you can see, we are each and every time we are getting a new shortest path, we are updating that. Okay.
Okay. Actually, we have to update each and every time. Actually, I just looked into like the one way B to C, C to A, D to D.
Okay, no. Basically, you have to apply this Dijkstra algorithm.
Okay, sir.
So this is how you apply the Dijkstra algorithm. So once you apply the Dijkstra algorithm, so you have to see how much time. So what is the minimum time it's taking to cover all the vertices? Okay. So
okay, sir.
So basically, it's 9 minutes. Okay.
Yes, sir. Thank you.
Yes.
Question number 11 means activity 11.8. Last question.
11.3. Question number 3, right?
Last question.
Last question.
4. It's 11.8. Question number 4.
11.
XYZ. There is a graph of XYZ.
11.8. Which one? 11.8.
Yes, sir.
Okay.
Activity 11.8. Last question. Question number 4.
Yes. Got it. Yeah.
These are in the slides, no, sir. SP5, SP4, that means shortest to 5, 4. That is given.
Is this one, right? This one.
Yes. This.
Yes. So yeah.
Yes,
so
sir.
Suppose the graph is shown.
In the graph. That is the answer, means basically.
So
it creates a cycle. So how can
this is actually it's given that this is a minimal spanning tree. Okay, this one is a minimal spanning tree of some graph. Okay, it is given that this is a minimal spanning tree of some graph G. Okay, so the thing is, what are the possible choices of G. Okay, so out of, so some options are given, which one of them can be G, or maybe so it can have more than 2 options correct, but I guess here only option D is correct. Okay, so
only option this option is correct.
Yeah, so one minimal spanning tree is given for some graph G. Okay, so you need to find the graph G. Okay, so my first question is whether this graph, so whether for this graph, this is the minimal spanning tree.
No, sir.
No, sir. It has cycles, sir.
Which one has
4,
cycle?
6, 8.
No, a graph can have cycle. Okay, so is whether I'm facing this problem, whether I don't know why your voice is not audible, like clear to me.
Okay.
No, can you repeat your question?
So graph, the graph was given is that all the only 8.
So I was saying this means there can be many things, right? We can say that we are having 1 to 4. There is an edge from 1 to 4 also. We can have edge from 1 to 0. There can be many possibilities.
Yeah, many possibilities. Yeah, correct. So this can be a possibility. Okay, right? This can be a possibility. Okay, this can be a possibility. Okay, there are so many possibilities. That's why the options are given. So out of 4 options, okay, you need to find the correct option. I'm not saying that this question has a unique answer. Okay, so you can have multiple graph. Okay, you can have multiple graph, and for all the graphs, you will have a single spanning tree. Okay, but here options are given, right? 4 options are given. Okay, so you need to find the correct option out of these 4 options. Okay, so my first question is whether this can be a minimal spanning tree of this graph.
No, sir. Because sir, there is an edge from 7 to 9 in the original tree, but it's not there in the this graph.
Yeah, so this is not possible because you don't have any edge here from 7 to 9, but you have a edge from 7 to 9 in your spanning tree. It's not possible. What about the second option?
No, sir.
Why?
Because sir, there is a edge in the original one. There is a edge from 7 to 10, but it's not there in this.
Yeah, correct. So here you have a edge from 7 to 10, but if you see in the original graph, you don't have any edge from 7 to 10. So this is also not possible. Okay. So what about the last one? Same. No, here you have a edge. So what argument you can give for?
There is no edge from 5 to 6 or 6.
6 to 5. So here you have no edge from 6 to 5, whereas you have a edge from here 6 to 5. Okay. So this is also not possible. Okay. So next thing is you have to check whether whether this is a minimal spanning tree for this graph or not. Okay.
Yes, sir, it's correct because all the.
Yeah, mostly you can check it, like you can apply, like you can see whether all the edges, whether this is a subgraph of this graph. Okay, the first condition, and second condition is whether this tree, whether this tree has included all the vertices of the last graph D.
Then can we say like this? If we have a tree, so if we superimpose on the graph, it will. There is no edge left.
Not edge, no vertices.
No vertices also.
Yeah. Basically, the term that you have used, it superimpose. So that is actually basically you can do it for a subgraph. So
okay.
So is it clear? Like whoever asked this question. Hello. Okay, so any so any other doubt?
Sir, I have
Okay, so one more thing, whether my voice is clear to you, because most of your voices are not clear to me. Like,
you're audible, sir.
Okay, I don't know then.
Sir, I have a doubt, sir.
Hmm.
Sir, can you little? I mean, I was many times confused, but about performing of BFS and DFS on directed and undirected graphs. So, sir, can we for this we can both apply BFS and DFS?
Yes. No, you can apply both BFS and DFS.
For undirected graphs, sir?
Undirected graph and directed graph.
Okay, sir. So if we perform BFS on a directed graph, sir, and we include any non-tree edges, and we found the BFS tree, and then we include any non-tree edges, can it also cycle, sir, like directed graph?
No, non-tree. So there is a classification of non-tree edges, right? You have a backward edges, you have forward edges, and you have cross edges, right?
Yes, sir.
So forward edges actually they actually form a cycle. Okay.
Backward edges.
Sorry. Yeah, maybe backward edges form a cycle. Okay. Forward edges and cross edges, they don't form a cycle.
Yes.
Yeah.
So, when we use, I mean, an BFS on an undirected graph, sir, sir, we found that including of any non-edges create a cycle because there is no direction. So there is no forward edges or backward edge. But
So then, since there is no direction, certainly you don't have forward. So forward edges and backward edges and cross edges, they come for a undirected, directed. Yeah.
So sir has explained, sir, about give an example on an in an directed graph and performing a DFS, and sir then explain the cross edges, forward edges, and
that he has explained for a directed graph, not for an undirected graph, right?
Directed graph, and sir applying DFS.
Yeah, DFS for a directed graph, you can apply BFS and as well as DFS.
When we are applying DFS on a directed graph, so that also give us the same result, sir?
No. Certainly you will have different thing, right? So for DFS, because DFS, the algorithm of that DFS algorithm is completely different from BFS, right?
Yes, sir. DFS for neighborhood search and BFS for level by level search.
Yes. So DFS is basically you are going into the deep. Okay, so once you reach, you forget about that vertex. Go to the next one. Okay, so but for DFS you are doing it level by level. So certainly fundamentally both the algorithms, they are completely different. Okay, so yeah. And certainly, I guess sir has not discussed anything about this forward and backward edges for BFS, right?
Yes, sir. That is the confusion, sir. That is sir.
Yeah.
From BFS on a directed graph, should we have same the forward edges, backward edges?
No. There is no such concept.
Okay, sir. Thank you, sir.
Yes. Okay. Any other doubt?
Yes, sir. Graded assignment question number 2.
Graded assignment question number 2.
The second question is,
Yeah.
At most, and at.
A minute, let me check. If G is a undirected graph such that every vertex has degree at most 2, right?
Yes,
Hello?
sir.
Yeah.
Yes, sir.
And the shortest path between any two vertices has length at most 2.
Yes.
Okay. Then find then what is the maximum number of vertices in G? Correct? This is your doubt, right?
Yes, sir.
Yeah. So let me try it. So G is a connected undirected graph such that every vertex has degree. Okay, every vertex has degree at most 8. Okay, and the shortest path between two vertices, okay, vertices has length at most 2. Okay. Then what is the maximum number of vertices in G? So have you tried to draw the BFS tree for this graph?
Yes, sir, but I don't understand how to. Sir, I tried, but I don't understand how to solve this problem.
See, the thing is, okay, let me write the question. So this is your question, right?
Yes, sir.
Okay, I wanted to share my writing. Okay, so so G is a given. It is given that D is a undirected graph, right?
Yes, sir.
This is the first thing, and second thing is
Every vertex is at most degree 8.
Degree 8. Degree 8. This is the second condition. Okay. Then the shortest path between any two vertices has length at most 2, right? The next thing is the shortest path is 2 between any two vertices. Okay.
Yes.
So the next thing is you have to find
maximum number of vertices.
Then what is the maximum number of vertices this graph can have? Okay. So okay, so let's say suppose you start with this vertex, right? Right. So
yes,
suppose this every vertex has at most 8 edges. Okay. So this is V1, right? So this is, so B1 can have at most 8 edges, right? So I can write this. If I draw the BFS tree, so this is, let's say you have a vertex B1 that has degree 8, because I cannot take 9. So at most I can take 8. So this is 1, 2, 3, 1, 2, 3, 4, 5, I guess. Then I can take 6, 7, and one more edges 8, right? So this is V2, V3, V4, V5, V6. Okay, let me take it V0. I'll start with 0. V1, V2, V3, V4, V5, V6, V7, V8, right? This is I can do according to the condition.
Sir, at most 8 in the sense, is it necessary to take 8, sir?
Because
at most is maximum possibility.
Max. So the thing is, we are also finding the maximum number of vertices.
That's why you have to take 8.
Yeah.
Understood. I thought that it is at most.
Yeah.
So we can take any number which is not greater than 8.
No. So since we are searching for the maximum value, always we have to consider the maximum thing. Okay. Once we reach to the maximum possible cases, then only we can get the maximum thing.
Yes,
and
sir.
one more thing is given. The shortest path is 2. Okay.
Yes, sir.
Then we have to take the maximum case. Right. Correct?
Thank you, sir.
Then we have to take the maximum. So now how many edges can go from V1? 8, not 8, because there is already
7.
7. So this is 7, right? So from V1 7 vertices can go, right? And from V2 also 7 vertices can go.
Yes, sir.
So again, similarly from V3 also 7 vertices can go, right?
Yes.
So now I cannot have any more further. I cannot further extend the tree, right?
Yes,
because it is given that shortest path, the shortest path is 2, right? If suppose I have one more here, so here suppose I have something H, right? So suppose I have a H from V1 to H, then again I have a branch which is coming out of H. Then I cannot have shortest path 2, right? From this vertex H1 to V0, the shortest path cannot be 2. It has to be 3, right? Yes. So I cannot extend it further, right?
Yes.
So only 7 vertices can come out of V1. Similarly, 7 vertices can come out of V2. 7 vertices can come out of V3. Okay. So then can you tell me how many vertices this graph will have?
7 into 56 plus 8 plus 1.
Yeah, 7, 56 plus
56, 7 into 8.
Yes, 56 plus
8
plus 1, right? So answer is 65, I guess. Yeah.
Sir, what is that 1, sir?
Sorry, 1 is V0. 1
V0.
is V0.
Okay. Number of vertices.
See, this is 1.
Yes, sir.
Right?
Yes, sir.
So here this is 8.
Understood, sir.
Yeah, correct. Okay, fine. Okay, so I guess, yeah. So anyway, we'll share the solution with you. Okay, I guess you'll get the solution by tomorrow, I guess.
Because so many doubts are there, sir, in the grade.
Yeah.
I lost some 4 to 5 questions.
So what about your previous mark? Like, have you so what? Probably, I guess you need 7.
Yes, something around 95 is there.
Okay, then no issue. Okay, but yeah, so the thing is, okay, you need to concentrate,
in the subject.
Yeah. So we have shared this week-wise weightage with you, so you can check
No, sir, I didn't get the.
No, we have shared with you today maybe around 6 or maybe 4. We have shared the week-wise weightage. You can check in the portal. Okay.
Week-wise revision lecture, sir.
Not revision. Revision lecture certainly will have it maybe in the next week. Okay. I'm saying week-wise weightage for the end sem. Okay. Yeah. Okay, then I'll stop the session now.
Okay, thank you, sir.
Yeah.
Thank you, sir.
Thank you, sir.
Yes, thank you.
Thank you, sir.
Yes.